Hello and welcome to the last new topic in section 6.5, which is going to be finding powers of complex numbers in trig form. And for this very first part here, you don't need to take notes unless you're particularly interested, because what I'm going to do is we're going to develop a formula for powers of complex numbers in trig form. To take a look, and we're not going to quite derive a formula, we're going to develop it by noticing a pattern. So if we want to find a complex number to the first power, it just is itself. Nothing happens. If we want to find a complex number to the second power, we can think of that as multiplying the complex number times itself. So if we have a complex number in trig form to the second power, that's this, the whole thing raised to the second power, it's just the complex number times itself. Well, we have a formula for multiplication from the last section. The formula for multiplication tells us to multiply the r's and to add the thetas. So in this case, the thetas are theta and theta. They're the same. So if we do theta plus theta, I can just write that as 2 theta. And then if we want to raise a complex number to the third power, there's a lot of different ways we could go about it. So if we want to raise this entire thing to the third power, one way to do it is to say we're going to raise it to the second and then multiply it times the complex number in trig form to the first. Because if we have something to the second power times the same thing to the first power, that's the same as raising it to the third. Well, we just figured out a formula for raising this to the second power. That's r squared cos 2 theta plus I sine 2 theta. Oops. And then once again, we now actually have a multiplication problem. So from our work in the last lesson, we're going to multiply these r's. R to the second times r to the first is r to the third. And then we're going to add the thetas. So if we have 2 theta and 1 theta, that's going to make the angle inside of cosine 3 theta and the angle inside of sine 3 theta as well. So I think you can start to see a pattern developing here, but we're going to do one more expansion. And to do that, I'm going to do the complex number to the fourth power. So for the fourth power, there's a bunch of ways we could break it down. I chose to do to the third power times to the first power, because we just figured out what this is to the third power. So if I pop this in there, r to the third cos 3 theta plus I sine 3 theta times r times cosine theta plus I sine theta, we can use our multiplication formula again. So I'm going to multiply the r's. R to the third times r to the first is r to the fourth. And then when we add the thetas, we're going to end up with 4 theta when we add the 3 theta and the 1 theta. So taking a look at this pattern, I think we start to see what's happening here. So we can predict what z to the fifth is. Z to the fifth is going to end up being r to the fifth times cosine of 5 theta plus I sine 5 theta. And if we wanted to find z to the sixth, it would be r to the sixth. So you take r, raise it to the indicated power, and then you multiply theta by whatever that power is. So in here, I'm not using the 6 as an exponent. It's a factor. It's being multiplied times the theta. And we can generalize what we have observed here using in a formula that we call de Moivre's theorem. So this is where you want to start taking notes if you haven't been taking notes yet. To find powers of complex numbers that are in trig form, we have what's called de Moivre's theorem. So if we want to raise a complex number in trig form to any power, let's call that n, we raise r to the nth and we multiply theta times n. So that's your formula. Let's go ahead and try a few problems together. For our first example, we're going to raise this to the 7th power. So here's my complex number in trig form. And if I want to raise that to the 7th power, then what we're talking about doing is taking this entire complex number and raising that entire thing to the 7th power. And to apply de Moivre's theorem, we're going to raise r to the indicated exponent, which in this case is 7. And then we're going to go in here and we're going to multiply our angle times the exponent. So since our angle is pi over 3 and the exponent is 7, we're going to do 7 times pi over 3. And that's just 7 pi over 3. Now, what we need to do next is we need to simplify this into standard form because the directions ask us to do that. So we have to figure out 2 to the 7th. You can do that off to the side. It's 2 times itself 7 times. And there's lots of ways to do that. A lot of you probably remember because you see it quite a bit in Algebra 2 class, that 2 to the 5th is 32. So if you know that as a shortcut, then you can jump down to 64 times 2, which is 128. And we end up with 128 for this number out front. And then to evaluate 7 pi over 3, cosine of 7 pi over 3 and sine of 7 pi over 3, we'll need to figure out where 7 pi over 3 is. We're going to have to sketch that. By the way, if we wanted our answer in trig form, we'd actually be finished at this stage. But since the directions say standard form, we continue. So 7 pi over 3 is going to go all the way around past 2 pi, and it's going to go past 2 pi by pi over 3. So it's going to be in quadrant 1, coterminal with pi over 3. Since that's in quadrant 1, both cosine and sine are going to be positive because all students take calculus. And if we evaluate the sine of the reference angle, since the reference angle is pi over 3, we can draw our 30, 60, 90. And the sine of pi over 3 is going to be radical 3 over 2. And the cosine of pi over 3 is going to be 1/2. This plus here is not actually necessary. I was just emphasizing the fact that we chose a positive for this. And the plus here is not necessary either. I was just, once again, emphasizing that we chose a positive. So if we now distribute the 128 in, we are going to end up reducing because 128 times 1/2 is going to be 64. And then here 128 over 2 is going to be 64. And this is our final answer in standard form. Let's continue on for a couple more examples. Our next example is going to be to find z to the 5th given this given this complex number in trig form. So one thing to observe here is that now we're working in degrees. The previous problem was in radians. This formula works in degrees and in radians. So we don't need any other formulas. We can just apply the same theorem here. And we want to raise this to the 5th power. I chose to use parentheses here. Last time I used brackets. They're the same thing. They're just grouping symbols. So if we want to raise this to the 5th power, we're going to have to raise r to the 5th power. And we're going to multiply 5 times our angle theta. And 5 times 10 degrees is going to be 50 degrees. So I'm able to simplify that pretty easily. That's 50 degrees. And since we want our answer in trig form this time, our last big task is to figure out what radical 3 to the 5th is equal to. So for radical 3 to the 5th, there are a number of ways you can go about simplifying. One way to do it is just to multiply out radical 3 5 times. Each pair of radical 3's is going to have a product of 3. So this is going to end up being 9 radical 3 out front. And the directions say to leave this in trig form, so we're going to leave it in trig form just like that. If the directions for this one asked us to go to standard form, we wouldn't be able to do that unless we had a calculator, because 50 degrees is not a special angle. So the only way we'd be able to evaluate cosine of 50 and sine of 50 would be using a calculator and getting a decimal approximation. We have one more example to do in this lesson, but it's a big one. So our final example is going to be to raise this to the 6th power. Now, if you notice, this is given in standard form. So one option we have here is to multiply this times itself 6 times. And I think we can all agree that that does not sound fun. 1, 2, 3, 4, 5, 6. That's a whole lot of distributing. So we're not going to do that. What we're going to do instead is we're going to rewrite 2 minus 2i in trig form and then apply de Moivre's theorem. So to rewrite this in trig form, that goes back to our previous lessons. We have those 4 steps. We want to plot, find r, find theta, and then write our answer, which in this case won't be the final answer. So to plot, we're going to be here in quadrant 4 because we're going right 2 and down 2. To find r, if you recognize that you have the ratios for 45, 45, 90, you can save yourself some time and jump right down to 2 radical 2. If you need to or want to do the formula for r, then that's totally fine. You're going to end up with the square root of 8, which is 2 radical 2, and you're going to end up in the same place anyway. To find theta, if you recognize the ratios for 45, 45, 90, and you're in quadrant 4, you actually could right away just go ahead and write 7 pi over 4. If you don't recognize that, no big deal. Just do your formula for tangent, which is b over a or y over x. So for this particular problem, tangent is going to be negative 2 over 2, which is negative 1. And for tangent to be negative 1, your reference angle is going to be 45 degrees. And again, we knew we were in quadrant 4 anyway, so we're still going to all work with 7 pi over 4 for our angle theta. So this complex number in trig form looks like this. Now, that in itself was an entire problem in the previous lessons. But for today, that's only part of the problem because our job was to raise this to the 6th power. So what we need to do next is use de Moivre's theorem. So de Moivre's theorem says if we have a complex number in trig form, which we do now, and we want to raise that to a power, what we can do is raise the r value to that exponent, and then inside multiply whatever theta is by the exponent, which in this case is 6. You'll want to reduce this. So if you want to reduce early, you can reduce the 6 and the 4 and make it 3 over 2. Let's do that. So that's going to be 3 over 2, which is going to make this 21 pi over 2 inside of cosine. Okay, so this time we have some work to do because the directions up there did say to give the answer in standard form. So there's 2 big things we need to do, and neither one's really that pleasant. So one thing we need to do is find out what 2 radical 2 to the 6th is. The other thing we need to do is figure out what sine and cosine of 21 pi over 2 are. You can do those in either order. I'll do this first. So if we have 2 radical 2 to the 6th, we could write out 2 radical 2 times itself 6 times, but that's an awful lot of work. So what I'm going to suggest is that we use properties of exponents, and since we have multiplication in here, we can rewrite or think of this as 2 to the 6th times radical 2 to the 6th. Using the powers of 2 that we worked with before, this is going to be 64. And then radical 2 to the 6th is going to come out to 8. There's a few ways to figure that out. One way to figure that out is to write radical 2 times itself 6 times. It doesn't take that long. Another way to figure that out is to think of radical 2 as 2 to the 1/2. Because we know when we have a square root, that's the same as a 1/2 exponent. And if we have a power to a power, we can multiply those exponents and get 2 to the 3rd. So that's how I got 8 here. Now, you can go ahead and multiply 64 times 8, but I'm actually going to leave them factored for now because I'm not sure if you've noticed, but in the previous problem, we end up reducing a lot in our previous problems because a lot of times we end up with fractions that allow us to reduce. So maybe I'll be able to reduce later and I won't actually have to figure out what 64 times 8 is. Let's find out. Now, for 21 pi over 2, you have some options. You have to find out what that's coterminal with. So one option is to sketch that large angle of 21 pi over 2. So remembering that every time you go 90 degrees, you've gone pi over 2, you can just count and keep track. It's going to be a lot, but we can count that. So that's 1 pi over 2. That's 2 pi over 2, which would be pi. This is 3 pi over 2. We know that one. 2 pi over 2. I'm sorry, said it wrong. So that's pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2, 11, 12, 13, told you it was a lot, 14, 15, 16, 17, 18, 19, 20, 21. Ugh. After all that, we find out we're coterminal with pi over 2. So the sign of 21 pi over 2 is going to be the same as the sign of pi over 2, which is 1. And the cosine of 21 pi over 2 is going to be the same as the cosine of pi over 2, which is 0. Now we're going to finish this problem in just a moment, but another way to do this, for those of you who did not want to sketch 21 pi over 2, because it was a lot, it's a lot to keep track of, we needed to find something that was coterminal. So to find something that's coterminal, if you want, you can subtract 2 pi, and you can subtract 2 pi as many times as you want. So if I do 21 pi over 2 minus 4 pi over 2, I get 17 pi over 2. And then I can subtract 4 pi over 2 again, because I can keep subtracting 2 pi as many times as I want. It's still quite a bit of work, because now you have to keep going. You have to do 13 pi over 2 minus 4 pi over 2. And then you'll have to subtract that from 9 pi over 2. And we're almost there. If we subtract 4 pi over 2 one more time, we get pi over 2. And all of these angles are coterminal to 21 pi over 2. But pi over 2 is the nice one that's coterminal. So you still get to the same place, whether you prefer to do the arithmetic here or you prefer to make your sketch. If you do have a large angle, you have some different ways to handle that. Now, I notice here that I'm going to have 0 plus 1i. And I had kept these factored before because I was hoping maybe I'd be able to reduce and not have to figure that out. But it looks like the time has come. I can't avoid it anymore. So 64 times 8 is going to be 512. And when we distribute that in, we're left with 512i. I told you example 3 was a big one. So it really was a lot of work. In order to rewrite this, in order to evaluate this and then write our answer in standard form, instead of multiplying this out 6 times itself, which you'd probably still be doing, to be honest. I know the process we did took a long time, but this might even take longer. We rewrote this in trig form. Then we applied de Moivre's theorem. And even though we had some larger numbers than we'd like, and even though we had a larger angle than we would like, we know how to evaluate and simplify to get our final answer. Thank you for listening. You can rewatch any part of these videos that you would like to. And at this point, you can move on to the next part of today's classwork.